Are you able to hear me? Good morning. Good morning to all. So we will wait for 1 or 2 minutes. Just as a preamble, today is a very interesting day because the date, just look at the date, it is 10/10/2020. So the date being so interesting, there is also another interesting fact, and that is about this year's Nobel Prize in Physics that went to Professor Roger Penrose, Professor Andrea Ghez, and Professor Reinhard Genzel. Now, why is this very interesting? It's a coincidence that in the previous lecture, I had just finished talking about galaxies, and I had mentioned that uh, all dominant galaxies in the universe that has been studied, they all have a supermassive black hole at the center. And precisely this year's Physics Nobel Prize went to Professor Andrea Ghez and Professor Reinhard Genzel because of their painstaking observation of Sagittarius A star, which is the center of our Milky Way galaxy, where a supermassive black hole with mass 4.5 million times the mass of the sun was discovered. So today's lecture, because it is naturally a continuation of where we left last time, namely galaxies, today we will talk about supermassive black holes, nature of black holes, and also late Professor Rai Chaudhry's contribution to the understanding of singularities. Now remember, all these are part of the syllabus of Introductory Astronomy course, except that they were in the later units, but because the day being special, just following the announcement of the Nobel Prize, I thought we can shift the unit to the present time so that it has relevance to the context regarding the Nobel Prize award. Right. So let's go uh, full throttle in today's lecture. Right. So, as you are all aware of the Nobel Prize in Physics that was awarded this year for the discovery that the formation of black hole is a prediction of general relativity uh, that comes out when one does a full mathematical analysis, and similarly for very accurate observation of the stellar motion around the Sagittarius A star, which is the center of our Milky Way galaxy. And these three scientists were awarded the Nobel Prize in Physics this year. Of course, the whole exercise started around 1915 when Albert Einstein, in order to make the theory of gravitation consistent with special theory of relativity, created the general theory of relativity. Now, of course, this is not a course on general relativity, so I'm not going to go into the details. Those who are interested in learning about general relativity thoroughly, they can study some very good textbooks which are available, like Bernard Schuld's The First Course in General Relativity, or Hartle's Gravity. Similarly, Weinberg's book on Introduction to General Relativity and Cosmology. There are many, many good books available on general relativity. Those who are interested can study it. Here, I would like to just point out that in Einstein's general relativity, the gravity is the gravitational force is actually not a force, but the appearance of gravity is essentially due to the non-Euclidean geometry of the space-time manifold, as shown in the uh, cartoon here, where Earth's gravity is not due to force, but rather the mass of Earth, it distorts the space-time geometry, and a typical test body around the Earth, namely a satellite, is going around the Earth because that is the shortest geodesic, and therefore there is no force, but the satellite is going around because such a trajectory is the shortest geodesic in this curved space-time. And what Einstein showed was that it is the energy and momentum of matter which essentially warps the space-time geometry, and the geometry of the space-time, it tells the test particle how to move about. All right. And in particular, Einstein deduced this theory of general relativity from an insight he had when he was trying to contemplate about the nature of inertial frames of reference, and suddenly it struck him that a frame of reference that freely falls in a uniform gravity, the gravity disappears in this freely falling frame if the gravity happens to be uniform. In other words, according to Einstein's theory, uniform gravity, that means the gravitational acceleration or the gravitational field being not only having the same magnitude everywhere, but the direction is also same everywhere. Such a state of gravity is actually no gravity at all, because in such a gravitational field, you can take arbitrarily large frames of reference, and if they fall freely, you can intuitively see very well that for an observer who in such a arbitrary large frame is freely falling in a uniform gravity, in the falling frame there is no gravitational force at all. If he drops objects, they will just hang, float freely. Similarly, he can't hold a pendulum and let the pendulum swing, etc. So, therefore, according to Einstein's gravity, which is the theory of general relativity, and theory of general relativity is nothing but a relativistic theory of gravitation, which incorporates the basic tenets of special theory of relativity. In Einstein's theory, it is the non-uniform gravity which is the true gravity. That means the tidal acceleration or the tidal force we discussed when discussing Newtonian gravity, because for a compact object, Newton's laws says that the gravity around a compact object is non-uniform, and therefore the quantity, if the compact object has a mass m, then at a distance r, the tidal acceleration, because of the non-uniformity, the tidal acceleration is given by gm by r cube. And if the test body has a size L, then the differential tidal acceleration that the test body will feel is of the order of gml by r cube. And it is this quantity which in Einstein general relativity corresponds to true gravity. In fact, those who have some knowledge about tensor calculus and general relativity, uh, she or he would immediately realize that gm by r cube is related to the Riemann curvature tensor around such a compact object. And it is the Riemann curvature tensor which is the hallmark of the non-Euclidean nature of the geometry of the space-time. Right. Don't worry if um, this particular aspect was not understandable. I included it just for the sake of completeness in order to talk about black holes. Now, the this year's Nobel Prize to Penrose for his significant work on singularity theorems in 1965, which were really amazing results. But one must acknowledge that Professor Roger Penrose's work on singularity theorems were essentially uh, hinged on the work of late Professor Amal Kumar Raichaudhuri, who used to teach in Presidency College, Kolkata, which currently is has become a university, so it's Presidency University. And of course, we know that astrophysical black holes as a meaningful idea came up only after Subramanian Chandrasekhar showed that there is an upper limit to the white dwarf mass. That is, the white dwarfs which supports against gravitational collapse by the degeneracy pressure arising out of Pauli exclusion principle for the electrons. Chandrasekhar, we have already discussed this in a previous lecture. What Chandrasekhar had showed was that if the white dwarf, which is supported by the degeneracy pressure of electron gas, if the mass of the white dwarf is larger than 1.4 times Sun's mass, then the degeneracy pressure will not be able to support, and therefore white dwarf must shrink because it cannot be maintained under hydrostatic equilibrium by the degeneracy pressure. This was around 1930, and around the same time, neutrons were discovered by James Chadwick. All right. As soon as Chadwick's discovery of neutrons were publicized, Landau, a versatile and an outstanding theoretical physicist, he immediately realized that just like electrons, neutrons are also fermions, and therefore Landau immediately worked out in a very simplified fashion the Chandrasekhar kind of result for a collection of neutrons, and he argued that due to stellar evolution, there could be stars where everything is in the form of neutrons and they are supported against gravitational collapse due to the degeneracy pressure arising out of Pauli exclusion principle applied to neutrons. And lo and behold, soon pulsars were discovered by Professor Jocelyn Bell, that time a PhD student of Professor Anthony Hewish. And Professor Anthony Hewish was awarded the Nobel Prize. Unfortunately, uh, Professor Jocelyn Bell was not given the Nobel Prize. One doesn't know why. But what was realized from this work was that the so-called neutron stars are indeed found in our cosmos. And particularly, just like white dwarfs have a critical limit, that of 1.4 times sun's mass, calculations show that the pulsars or the neutron stars would also have a critical limit, and the upper limit to a stable neutron star has been um, theorized to be in the regime uh, 2.5 to 3 solar mass. The uncertainty is due to the fact that the nuclear equation of state is not known at the densities which are likely to be there for neutron stars, namely density of the order of 10 to 14 grams per centimeter cube. At such high densities, one doesn't know what is the nuclear equation of state. And that is the reason, unlike the white dwarf upper limit, the neutron star upper limit for mass, there is an uncertainty. It could be anywhere from 2.3 solar mass to about 3 solar mass. But nevertheless, what the uncertainty notwithstanding, what the work tells us is that if after passing through the white dwarf phase, reaching the neutron star phase, if the neutron star mass is larger than 3 times sun's mass, even the degeneracy pressure of the neutrons will not be able to support against the gravitational collapse, and such a heavy neutron star will simply collapse to form a black hole. So, in other words, from Chandrasekhar and Landau's work, we know that for very heavy stars, black holes are the ultimate reality. But then, around 1955, late Professor Amal Kumar Raichaudhuri, when he was trying to understand the Big Bang singularity, that is, the universe according to the Big Bang model started when the universe density was infinite, the temperature was infinite, density was infinite, and in particular, if one calculates the Riemann curvature tensor at the beginning of our universe, the Riemann curvature tensor components also become infinite. So Amal Kumar Raichaudhuri was trying to understand when can there be a singularity, and he developed an equation which is today known as the Raichaudhuri equation, and it was the use of Raichaudhuri equation that led Professor Penrose and late Professor Hawking to develop powerful theorems concerning gravitational collapse. And the conclusion was that any gravitational collapse of a of a collapse of a compact object will lead to singularities if the energy density plus 3 times pressure is positive. It's called weak energy condition. That is, the weak energy condition says if the collapsing object satisfies the condition that energy density plus 3 times pressure is positive, then the collapsing object must collapse to an infinite density, or in other words, there is a singularity. Actually, there are more technical concept concerning singularities that Professor Penrose developed, like geodesic incompleteness, closed trapped surfaces, but those are technical aspects, and I will not discuss them in this lecture. Of course, before all these singularity theorems that first Penrose proved in 1965 and later Hawking and Penrose built over that and proved several singularity theorems, the early people who actually thought of black hole like solution even before general relativity was a bishop whose name was Michel, and then immediately by Laplace. And then, of course, after general theory of relativity was proposed by Einstein in 1915, within few months, Carl Schwarzschild, who had received a copy of Einstein's paper, Schwarzschild immediately gave the first exact mathematical solution from which a black hole like solution emerged. And then Roy Kerr, he developed, he obtained an exact solution for rotating black hole. And then Reisner and Nordstrom, they obtained rotating charged black holes. And interestingly enough, there's a little known general relativist S.D. Majumdar, who in 1947 and independently Papapetro, these two gentlemen, they obtained in 1947 an exact solution to static charged black holes, many of them together. That means multi black holes, each carrying charges so as to uh, maintain a static condition, balancing against the gravitational attraction through electromagnetic repulsion. And such an exact many black hole solution was obtained by S.D. Majumdar and independently by Papapetro, and it's called Majumdar-Papapetro solution. And then, of course, there is Vaidya solution, where late Professor E.C. Vaidya talked about uh, a collapsing object from which uh, zero rest mass particles are coming out radially. So, as you can see, that the Indian general relativists were uh, also very early on had caught on to exciting research in the field of general relativity. Now, we have already said that Milky Way galaxy at the center being termed as Sagittarius A star, has a supermassive black hole weighing 4.5 million times heavier than our sun. And this is, of course, an artist's rendering of what Milky Way galaxy would look like if it is viewed from edge on. All right. And our solar system is somewhere here, which is 8 kiloparsec from the supermassive black hole at the center. And as you can see, the spiral arms are in the disk regions of our Milky Way galaxy. There is a galactic bulge also in the nuclear region where the stars are moving in eccentric orbit around the supermassive black hole. And of course, there is a big halo of dark matter. All right. Now, remember that I have given you an assignment sheet where I have listed few problems, and for the problems you need to work out numbers, and these numbers are very important, and therefore let us again review what are the typical numbers we are, from observational point of view, very confident. One is sun's radius, which is equal to 6.96 times 10 to the power 10 centimeter, or if you want to get it in meters, then it's 6.96 times 10 to the power 8 meters. One astronomical unit. One astronomical unit is basically the average distance between Earth and the Sun, and this average distance between the Earth and the Sun is 1.496 times 10 to the power 13 centimeter, or equivalently 1.496 times 10 to the power 11 meters. Similarly, the solar mass, the solar mass in astronomy community is denoted as M with a subscript where there's a circle with a dot. So in the assignment set problems, wherever you see the symbol capital M with a subscript, circle with a dot, you know that it refers to sun's mass. And sun's mass is about 2 times 10 to the power 33 gram, or 2 times 10 to the power 30 kilogram. And we have already talked about parsecs and kiloparsecs. For the sake of completeness, let me again repeat that 1 parsec, which is about 3.26 light years, is equal to 3 times 10 to the power 18 centimeter, or 3 times 10 to the power 16 meters. And 1 kiloparsec is 1000 parsec, so which is about 3 times 10 to the power 21 centimeter, or equivalently 3 times 10 to the power 19 meters. All right. Right. Now, let us talk in a very simple way how from Newtonian physics we can talk about black holes. And this is what Michel in the 18th century had done. What Michel argued is the following. He essentially looked at the escape velocity from a spherical object. So imagine that you have an object of mass capital M and radius capital R. So imagine that you have any object of mass capital M and radius capital R. All right. And we all know that if we are standing on such an object, and you can, for the time being, think of this sphere being our Earth, and we know that if we throw any object in the upward direction, it eventually comes down. So as we play cricket, sometimes for fielding practice, we throw the ball very high up and try to catch. And every one of you, I'm sure, would have done this exercise. And very often, some people have very good ability to throw balls to extremely high, uh, to very large heights, and then we sort of follow through and try to take the catch. But I'm sure no one would have found a cricket teammate who could throw a ball in such a way that the ball never comes back, it escapes. Now, it is possible, of course. There is no reason why it is not possible. And physics can tell us what should be the escape speed and how do we estimate. The answer is very simple. Let us go back to our basic school level uh, Newtonian physics dealing with gravity. We all know that if we have an object, spherical object of mass m, then at a distance d, if you have any test particle of mass small m, imagine if you have a test particle like that of a ball, cricket ball, and whose mass is small m, then any such test particle with mass small m and at a distance d from the center of the earth will be exerted upon by an attractive force due to earth's gravity, and the magnitude is g capital M multiplied by small m divided by d square. That is the Newton's inverse square law of gravity. So m being the capital M being the mass of the ball, mass of the big sphere, and small m being the mass of the test body like the cricket ball, and the distance is d, then the gravity acting on this test particle, the magnitude of the gravitational force which is directed towards the earth would be g capital M small m divided by d square. Now we can work out from the force what is the potential energy for such an object. That is worked out by saying, well, if you want to carry that object from here, from the surface to a distance d, how much work would be required? And one can easily calculate the amount of work needed to get the ball at a distance d. And the answer is capital G, which is Newton's constant, into capital M multiplied by small m divided by d. That is the work done. And because gravity is attractive, the potential energy, if you say that the potential energy at infinity is zero, then the potential energy at a distance d will be minus capital G, capital M, small m divided by d. All right. Remember that potential energy can be arbitrarily added to any constant number. So when I say that the potential energy at a distance d is minus g capital M small m divided by d, I have assumed that the potential energy at infinity is zero. All right. In other words, to take the object from the at from a distance d to infinity, I have to spend an energy g capital M small m divided by d in order to send it to infinity. All right. Good. Now, how do we calculate the escape velocity from such an object which has total mass capital M and radius capital R? Suppose the object was at the surface of the test particle. Suppose test particle, like a cricket ball, is on the surface of the object. Then what will be the gravitational potential energy? Just now I said that if the object was at a distance d from the center of the mass, then the gravitational potential energy will be minus g capital M small m divided by d. But when it is at the surface, the distance is r, capital R. So therefore, the gravitational potential energy of an object on the surface of the massive object is minus g, capital M, small m, divided by the radius of the object. And what do I want to do? I want to find out the minimum speed v with which I should throw my cricket ball in the upward direction so that it never returns. All right. That means I have to give it a kinetic energy. So the kinetic energy, if I throw the object with speed v from the surface, then in the beginning, the kinetic energy is half mv square, and the potential energy at the surface minus g, capital M, small m by capital R, and this is the total energy. All right. So when from the surface of the massive body I throw an object with initial speed v when it was at the surface, so that initial distance from the center was capital R, then the total energy is kinetic energy plus potential energy. And in this case, it will be therefore half mv square minus gmm by capital R. And what is the minimum speed with which I should throw that it never escapes, it never returns? Clearly, if this total energy is zero, then it will never return. How do I say that? Remember, it is going, when will the total energy be zero? As the object is going away from us, as it is receding, the distance d of the object from the center is increasing. And I want that the object, when it goes to infinity, that means d becomes infinity. At infinity, the potential energy becomes zero. And the minimum speed is that at infinity, when it reaches infinity, that time the speed also must be zero. That's the minimum initial speed requirement. That means when the total energy, when I flung the object outwards, if I made sure that the total energy, kinetic energy plus gravitational energy was zero, I'm sure that that is the minimum speed with which I should throw in order that the object goes to infinity. Okay. And from this equation, as you can see, half mv square should be equal to gmm by r. Small m gets cancelled both sides, and therefore half v square is gm by r. In other words, the escape speed v is simply square root of 2gm by capital R. Okay. All right. Now, let me pause for a while and see if there are any questions. Are there any questions so far? So, those who are not physics MSc students, have I been clear so far? Are there any questions? Looks like there are no questions, so we can continue. Okay, there's a question by Shubham. Well, what does one mean by bending? So, for example, if we take a uh, okay, thanks, Shruti. Let me first answer Shubham's um, question. When we bend a sheet of metal, all right, we apply physical force and we can bend it. But how do we know that the sheet has got bent? By visual inspection, we can say, oh, it has bent. That's because we are not sitting on inside the sheet. But suppose an ant was crawling on the sheet, this metal sheet. Initially, the metal sheet was flat. And now I have bent the metal sheet in such a way that in a small region, the sheet has a spherical kind of bend. Question is that will an ant be able to figure out whether now the sheet has got bent? Okay. And indeed, the ant can do that because when the metal sheet was flat, then if the ant had drawn triangles on the metal sheet, the sum of the angles of the triangle, he would have found it to be 180 degrees. Because when the sheet was flat, Euclidean geometry holds good. And in Euclidean geometry, we can prove a theorem which is the sum of the interior angles of a triangle is 180 degrees. Now that an external agent, namely I, have caused a spherical bending in some region of the sheet, the ant can go to that region and draw a triangle, and you can show very easily, convince yourself that when you draw a triangle on a spherical surface, what do I mean by triangle on a spherical surface? Take 3 points which are not collinear and join them with straightest possible lines. Straightest meaning shortest possible line. It will not be straight compared in comparison with flat space, but take 3 non-collinear points and join them with shortest segments. That is a triangle by definition, and you can convince yourself by taking a globe and drawing triangles on it that on a spherical surface, the sum of the interior angles of a triangle is actually greater than 180 degrees. So therefore, the ant can establish that indeed the metal sheet over which the ant was crawling is no longer flat. It has been bent. Well, knowledge of tensor calculus and differential geometry helps you to do similar kind of analysis when you go to 3 plus 1 dimensional space time. I gave you an example concerning a 2-dimensional surface because we all know about Euclidean geometry on a flat surface. But if you want to do such exercise like what you have asked, how do we bend space time? You have to learn tensor calculus, and I mean, in some cases, if one learns differential geometry, one gets a better view about the curve space time. And what Einstein showed was that it is the energy and momentum of matter which causes the curvature of the space and time. Regarding Ankit's question, I will soon come to it. I have not yet talked about the so-called event horizon radius and why light can't escape from black hole. So far, we have only calculated the escape speed. I'll soon talk about black holes. All right. Medha has asked, can we access the other side of space-time curve? I don't understand what you mean by other side of a curve. A curve is a curve. A curve, by definition, whether it is in three-dimensional space, two-dimensional space, or four-dimensional space-time, a curve, by definition, is locus of all points which can be parameterized by a single real number. In other words, a curve is a one-dimensional set of subset. It's a one-dimensional subset of a higher dimensional space-time. So I don't understand the question, uh, the other side of space-time curve. Can you be more clear, Medha, as to what you want to ask? All right. I mean, maybe at the end of the lecture, Medha, you can sharpen your question. All right. Good. Now, let us go to the lecture. Yes, Shubham, any mass can locally cause the geometry of the space-time to have non-Euclidean nature. Even an electron can do it, but the extent of the space-time curvature will be tiny. So, Earth, so what is the thing that causes a high degree of space-time curvature? It is actually the density. More is the density, more compact is an object. Just outside the compact object, the space-time curvature is more. So the crucial thing is the density of a compact object tells us how much curvature is associated with the space-time geometry. Okay. All right. So let us go to the lecture. All right. So we have established by simple argument that the minimum speed that is required for an object to reach infinity, if initial speed with that was given is v, that minimum speed is square root of 2 gm by r. And this calculation, we do it very often in our school curriculum, and it's called the escape velocity. And for Earth, the escape velocity is about 11 kilometers per second. All right. If you put in the value of Earth's mass and radius of Earth, the number you get is about 11 kilometers per second. So I give an exercise to everyone. So note, the exercise I have given it to everyone is to take this expression square root of 2 gm by r and find the escape speed from Earth, from Moon, and from the surface of the Sun. Repeat, I have given you now an exercise to calculate the escape speed from the surface of the Earth numerically using this expression, from the surface of the Moon, and from the surface of the sun, and then argue from this result why moon doesn't have an atmosphere. So calculate the three escape velocities and argue that why is it that there is no atmosphere around moon. Okay, right. Now Michel in 18th century, he argued, Michel had already learnt his Newtonian physics. He asked the following question: can we have an object whose mass is of course capital M, but its radius r is so small that the escape velocity becomes the speed of light? That's the first time someone asked this question, that can we have objects of mass m but radius so small that the escape velocity is speed of light? That means if the object becomes even smaller, even light can't escape. That means what? All I have to do is in the expression for the escape velocity, I substitute v equal to the light speed and calculate what is the size of an object. If c is equal to square root of gm by rs, then obviously you square root, if you take the square on both sides, c square becomes 2gm by rs, and therefore rs becomes simply 2gm by c square. In other words, what Michel and later on Laplace also did similar calculation, what they showed was that if an object of mass m contracts to a radius rs which is equal to 2gm by c square, then only signals that can escape from the surface are signals which move with speed c. That means with speed 3 times 10 to the power 8 meters per second. Obviously, both Michel and Laplace realized if the radius of the object becomes less than 2gm by c square, even light cannot escape, because escape speed is inversely proportional to square root of r. If r becomes smaller, for the same mass, the escape speed becomes larger. So Michel and Laplace therefore proved that for an object of mass m, if its radius becomes smaller than 2gm by c square, even light cannot escape from the surface of such an object. Now, this is a very amazing result that this immediately tells, of course, this tells us that nothing can escape from such a compact object, because special theory of relativity guarantees us that nothing can move with speed c unless their rest mass is zero, and furthermore, nothing can move faster than the speed of light c. That follows from the relativistic mass equation. As you know, in special relativity, we prove that the relativistic mass is rest mass divided by square root of 1 minus v square by c square. From that, we know that only those particles can move with speed c whose rest mass is zero. And in particular, m0 by square root of 1 minus v square by c square tells us that no particle can move faster than c, because if anything moves faster than speed c, square root of 1 minus v square by c square becomes imaginary. All right. So that's the problem. So Michel and Laplace's argument gave the first hint of objects from which nothing can escape. Okay, very good, Ankit. Good that you have calculated the Earth's escape speed from Earth. And what I suggest is that everyone should do the calculation for Earth, Moon, and Sun. Calculate the escape velocity. I can see there's another question. Yeah, but the example of ant I gave was a mathematical result concerning the curvature of a two-dimensional surface. Now, you have used words like fabric, gravity bending fabric, but these are words. Space time is space time. It's not a fabric like uh, the fabric of my kurta or the fabric of a shirt. These are all words. Okay. The real way to understand the curvature of the space time is through mathematics. As I have written articles and I have also mentioned in several lectures that when we learn advanced physics like quantum theory, relativity, particle physics, then our day to day senses, like the feeling of hardness when we touch a solid, the feeling of wetness when we talk about liquid, these are related to human mind, human body, human feelings. But the laws of nature are beyond human beings. The laws of nature do not care whether human beings exist or not. And so far, for example, in our neighborhood, Earth is the only planet which has human beings. But a vast region of our stellar system has no intelligence. And natural laws are therefore all about the real physical world, and they do not necessarily have to be tied by languages that were developed by human beings. Languages are artificial. That's the reason why different local region will have different language. But the physical world must have a universal language, and that is the language of mathematics. The language of the physical world or language of nature must be free from contradiction. It should be logical and it should be based on numbers. That's because our measurement of quantities, they are in terms of numbers. So therefore, any language that is logical, free from contradiction, and based on numbers, they necessarily, that language must be mathematical in nature. And that is the reason why we see the laws of physics are mathematical. You might, uh, those who are interested in knowing why mathematics is the lingua franca for nature, you can read two articles which I have written. If you just type in mathemagical 2014 in the Google, you'll see my article. And similarly, if you want to read another um, article regarding mathematics, I can send you later the link. But what I'm trying to say is that words, analogy, they have a limited purpose. They can make you have an intuitive feeling. But real way to understand the curvature of the space time resulting from energy and momentum of matter, you have to learn tensor calculus and do a course on general relativity. So, I'm just giving you some links. So, if you want to learn about general relativity, so for okay, so let us carry on with our lecture. All right. So, from the escape velocity argument itself, with the combination of Newtonian gravity and a result from special relativity that nothing can move faster than the speed of light, we established that there are such objects which are such that when their radius shrinks below 2 gm by c square, then even light can't escape from such objects. So, from Newtonian physics itself, we can argue about existence of black hole like objects. But of course, to get a much more precise understanding of black hole like objects, we must study general theory of relativity. Good, let's go further. So this is the so-called radius, and it is called the Schwarzschild radius because Carl Schwarzschild was the first person to get an exact solution, and he commented on object having a size less than 2 gm by c square and the peculiar things that happen. And here is a cartoon of the so-called black hole. But of course, what I'm going to say now is pure general knowledge in the sense that I'm not deriving all these. To derive all these, you have to do a course on general theory of relativity. So, what emerges from general theory of relativity is that if you take a spherical body of mass m and if you compress it to a size less than 2 gm by c square, then such a spherical body necessarily collapses to a single point. And this single point, because the entire matter collapses to a single point, tells us that the density has become infinite. And thereby, clearly, it is a singular object. Singular because density has become infinite. The components of Riemann curvature tensor becomes infinite. Okay. And why are infinities not liked by physicists, because all laws of physics are in the form of differential equations, and to solve differential equation you have to give initial conditions, or you have to set up the boundary condition, and infinite numbers cannot be used as boundary condition or initial condition, and therefore predict- predictability gets lost when quantities become infinite. So the differential equations cannot be used when physical quantities become infinite. But what is very interesting is, which resulted from Carl Schwarzschild work, that a spherically symmetric object, when it collapses to a point, this point, of course, is singular, but it is covered by a mathematical surface. This mathematical surface, two-dimensional space-like surface, has a radius 2 gm by c square. And the important quality of this mathematical surface is mathematical surface acts as a one-way traffic. That is, any event that happens outside the mathematical surface called the event horizon, any event happening outside, we can know about it. Outside observers can know about it because light from that event can reach us. But any event that happens inside the event horizon, we can't know about it because a light ray from such an event, if it starts outward, it'll fall back. It can't come out. We have already seen the reason from very simple Newtonian physics. And furthermore, it is a one-way traffic. Objects can come from outside, cross the event horizon, and go to the singularity, but nothing can come out. So, this mathematical surface called the event horizon acts as a one-way traffic. Okay? And such a black hole is called Schwarzschild black hole as a mark of respect to Carl Schwarzschild, who got an exact solution few months after Einstein gave his general theory of relativity. And because of his participating in the First World War, he developed some illness and died very shortly afterwards. Right. So here is another cartoon that since anything that goes inside the event horizon, it necessarily has to reach the singularity, it cannot escape. And the diagrams like bending of the space-time is just for visualization purpose. But as I said, to get a good understanding of black holes, one must take a course on general theory of relativity, which according to many physicists is one of the most beautiful theory ever constructed. Following After that follows Maxwell's electrodynamics. There is another way of talking about the event horizon, and that is the waterfall analogy. So here again, I am giving the image credit to M. Strassler 2014 because this I have taken from the internet. So I have to give due credit to the original contributor. So imagine that there is a waterfall region. So water is flowing along a slope. So water from the left is coming, and as it proceeds towards right, its velocity keeps on increasing because of the slope. And finally, there is a precipice because of which the water falls. Now, not everywhere the water velocity will be same. After all, due to viscous force between the banks of the river, the water velocity near the banks would be smaller compared to the central region. The central region of the river, the water will be flowing faster, while near the bank at the same point, the water velocity will be slower because there is a frictional or viscous drag between the solid region of the bank and the water. Suppose I am in a motorboat, and the motorboat in still water can move with a maximum speed of, let's say, 100 miles per hour. That's the maximum speed. Okay. Because every vehicle has a limitation. It can't move beyond certain speed limit. So I'm sitting in a motorboat that, with respect to still water, can only move with a maximum speed, let's say 100 kilometers per hour. Okay. Ask the following question, that when can up to rather up to which point can I go in my motorboat and be safe? That's the question I'm asked. Safe meaning what? That I want to avoid being dragged along the waterfall, because if I fall with the waterfall, that's it, that's my end. So therefore, I must know till what point I can move around in my motorboat in a very safe manner. The answer is very simple. Find out all the points on the surface of the river where the velocity is 100 kilometers per hour. Okay? And you will get such a line. This dotted line is such a line. Note that the line extends towards the waterfall along the banks, but in the middle, the line is further away from the point of the waterfall. Why? Because, as I mentioned, the speed of water is maximum at the central region, but at the bank, the speed is lower because of the viscous drag exerted on the water by the banks. Okay. So this dotted line is the locus of all points where the water velocity in this direction is 100 kilometers per hour. Of course, the moment you cross this dotted line, the water velocity is greater than 100 kilometers per hour. All right. Now, therefore, we know that my water boat, with respect to water, can at the most move with a velocity 100 kilometers per hour. And that's a crucial phrase, with respect to water. So my motorboat can move at the most with a speed 100 kilometers per hour with respect to the water. Clearly, if my motorboat crosses this dotted line, then that's it. I cannot cross the dotted line in the opposite direction. Why? Because with respect to the water, I can move in the opposite direction at the most with a speed 100 kilometer per hour. But once I've crossed the dotted line, the water in the river itself is moving towards the right with a speed more than 100 kilometers per hour. Therefore, with respect to someone on the bank, the water is moving more than the speed 100 kilometers per hour, and I am, with respect to the water, is moving in the opposite direction with 100 kilometers per hour. But for the observer on the bank, he will see that I am slowly moving to the right, because according to him, my speed is simply 100 kilometers per hour minus the water velocity here, and that will be negative. And hence, the observer will see that once I cross this line, I necessarily move in this direction and go along the waterfall and perish. In other words, this dotted line acts like a Lakshman Rekha. Once I cross this Lakshman Rekha, that's it. The waterfall will act as a Ravan and I disappear. So this dotted line is like the event horizon of a black hole. So I always uh, sort of feel that this is a better analogy of an event horizon. By the way, this is only an analogy. The real event horizon, there is no water, there is no waterfall. So this is only to be taken as an analogy. Let me see if there are any questions, because I have said a lot of things. Are there any questions so far? Because today's lecture is somewhat of more abstract concepts, and therefore I must pause and take a stock of the situation. I hope my lecture is not going above your head, because these are concepts which are not encountered in our day to day life. So Priyanka is asking, what is the present condition of black hole? It depends which black hole are you talking about. So as I said, that the event horizon of a black hole acts as a one-way traffic. So if there are a lot of matter around the black hole, and a fraction of the matter will be crossing the event horizon and falling onto the black hole. So therefore, the black hole's mass, like our supermassive black hole at the center of our Milky Way, its mass will be steadily increasing. Okay? So any black hole which is surrounded by gaseous environment, any astrophysical black hole, that is, black holes with mass greater than sun's mass, if it is embedded in a region where there is lot of matter, the matter would keep on crossing the event horizon and reaching the singularity, and therefore the mass of the black hole will keep increasing. So all astrophysical black holes tend to become heavier and heavier by swallowing the ambient matter. Okay? All right. So let us continue with the lecture. So I hope I have given you a flavor of the notion of event horizon. Let me skip this slide because this has many more technical aspects, and I will skip this slide. A natural question which some of you might ask is, well, if there is an event horizon, so that anything that happens below the event horizon can never be known to an outside observer, how will we know whether a dark region in the sky has a black hole or not? Because black hole, the event horizon will make a black hole completely dark. How will we know that whether there is a black hole somewhere or not? Well, the oldest indirect evidence of an astrophysical black hole came out by studying the X rays from an object which is called Cygnus X1. Now, it turned out that Cygnus X1 is a binary star where there is a normal star going around a very massive object which was which itself was not seen as a star, but huge amount of x-rays was coming from the region, and moreover the luminosity in x-rays was fluctuating over very tiny time scales. All right, now this is very important, that not only the Cygnus X1 source, astronomers found that there was a normal star going around some point which itself was not seen as a star, but the system was emitting in X-rays in a copious manner, and the X-ray luminosity was fluctuating very fast on time scale shorter than 1 second. And immediately astronomers therefore inferred that the X-rays must be coming out of very hot matter going around a black hole. So the model was as follows, that there is a black hole and the normal star was orbiting around the common center of mass constituted by the black hole and a normal star. And because the normal star is rotating, the matter from the normal star, which was flowing out due to the gravitational pull of the black hole, it could not radially fall because of the angular momentum. And therefore, the matter from the normal star, as it fell towards the black hole, it formed a disk around the black hole. And we know already from Kepler's laws that any object which is closer to the center, massive center, would be moving faster. Remember the third law of Kepler's, which says square of the period is proportional to the cube of the distance. So if it is closer, period is smaller. Period smaller meaning speed is larger, because 2 pi by period is the angular frequency, and radial distance times angular frequency will be the speed. So closer to the black hole, the speed of this gaseous matter will be higher compared to further away, and therefore there's a gradient in the speed. The speeds at different distances are different, and because of the gradient in the speed, there is a viscous rubbing between elements of the gas, and because of the viscous rubbing, because the different parts are moving with different velocity. Rubbing of gaseous elements make the gas going around the black hole very hot, just like when we want to warm up our palms in the winter, what do? We rub our palms together. Rubbing, what does it do? Because of the frictional force, when we rub, the kinetic energy of the palms get converted into heat energy because of the dissipative force like friction. Here, similarly, the differential velocity of the matter, they lead to heating of the matter, gaseous matter, due to viscosity. And the whole disk becomes very, very hot, so hot that they start emitting, they become in a plasma. Essentially, this so called accretion disk is essentially in plasma state. That means maximum fraction of matter is in the form of ions and electrons. They are very hot. And such a system of hot plasma emit in X-rays if the temperature is more than 10 million degrees Kelvin, then they start emitting in X-rays. And by seeing the X-rays fluctuating on time scales less than 1 second, one also infers the size of the accretion disk. How? Because special relativity tells us that nothing can move faster than the speed of light. And if the emitting region is fluctuating with scales, time scales less than 1 second, then size of the emitting region cannot be larger than speed of light into 1 second, because emitting region must be moving about in order to cause fluctuation, and no motion can have speed greater than speed of light c. And the fact that the emission is fluctuating over time scales less than 1 second, therefore size of the region that causes fluctuation in the X-ray luminosity must be less than c into delta t, and here delta t is less than 1 second, so therefore its size is less than 3 into 10 to the power 8 meters. And from the orbital motion of the star, one infers that the object, which cannot be seen as a star, has a mass of the order of 15 solar mass. Okay? And therefore, this object must be very, very compact. And therefore, indirectly, any object whose mass is 15 solar mass and it is so compact must be necessarily a black hole. So that was the first indication of a black hole. By the way, I give you further exercise. So go back to the event horizon size. The event horizon size is 2gm by c square. Work out the values of this event horizon size for sun by putting m equal to 2 into 10 to the power 33 gram. Work out what is the event horizon size. Take it as an exercise. Similarly, if m were to be 30 times heavier than sun, that means 30 solar mass, work out what is the event horizon size. Similarly, if m is 15 solar mass, work out the event horizon size. And finally, if m is 4.5 million solar mass, work out the event horizon size. Why did I give you the exercise for 4.5 million solar mass? Because That is the mass of the supermassive black hole that lies at the center of our galaxy, which was discovered by Andrea Ghez and Reinhard Genzel, for which both of them shared the Nobel Prize this year with Roger Penrose. So do these exercises so that you get a feel for the numbers. Because remember, as I said, science is based on measurements. All measurements give you numbers. And unless you work out the numbers, you cannot get a full feel of the scientific subject that you're learning. So please work out these numbers so that you have a good handle on the size of the event horizon for different scale black holes. Right. So in the past, signature of an astrophysical black hole was intense high energy radiation that was fluctuating within short time scale. But there is another way of finding out whether there is a black hole somewhere, and that is if there are test particles going around the black hole, then monitor the speeds of the test particle. And using the Kepler law, you can estimate what is the mass of the black hole. And if your test particles, their radial distance from the central mass is very, very tiny, and yet the mass is very large, you will get an indirect evidence of massive black hole. By the way, I hope all of you have done that exercise, the two exercise problems I had given you in my previous lecture to estimate the mass of Earth using the orbital motion of the moon around Earth, and similarly mass of Sun by using the orbital motion of Earth around Sun. So we are saying use the same principle to detect whether there is a very compact but very massive object which could be a black hole. All right. Right. So for the Cygnus X1, as I told, there's a cartoon of how there could be fluctuation in the uh, X-ray luminosity. So that there is a disk of plasma, hot plasma going around, a blob of hot plasma, okay, here breaks off and it falls towards the black hole. So such a thing can constitute a fluctuating X-ray luminosity. And because the blob cannot move faster than the speed of light, the variability time scale delta t, c into delta t, where delta t is the variability time scale, gives you a size of the emitting region. And that is one of the standard methods to infer the size of black holes of any source that is emitting intense radiation and fluctuating over tiny scales. I will skip these slides concerning rotating black holes, for which Penrose discovered a very interesting manner by which you can derive energy out of the rotational energy of a black hole. I'll not talk about it. Let me skip this slide also. Right. So again, let's go back. I've already told you there are all kinds of galaxies. So this is a spiral galaxy which is being viewed edge on. And as you can see, there's a bulge and the spiral arms are confined to the disk region. And you can see the dust lane. The dust, as I have told you earlier, the dust grains absorb visible light and re-radiate in infrared, and that's the reason why the dust lanes appear dark. Here is another Aegean spiral galaxy. Again, you can see the bulge, the disk region. And again, this has a black hole at the center. But how did the existence of supermassive black holes came to be known? We'll come to it. But before that, this is a spectacular spiral galaxy which is almost presenting itself face on. And the bulge region is this, the disk region is where the spiral arms are. It's a magnificent spiral galaxy that happens to be uh, face on to the line of sight. And here are examples of elliptical galaxies, which are triaxial spheroids, which are essentially smooth. The density of the stars are higher at the core, but as one goes outwards, the density of the stars fall. Now let's come to the Nobel Prize 2020 in physics. And this is the work which independently by Andrea Ghez from USA and Reinhard Genzel from Germany, they did independent observation. Remember, this is something I must point out, which is very important in science. In science, if I do an experiment and tell the entire world that, look, I have done this experiment, these are my results, that is not sufficient. There should be independent groups which do the experiment, and they should be able to see the same thing that I have seen, and my conclusion that I have obtained, they must also get the same conclusion. If this doesn't happen, then most likely my experimental result is either wrong, or I have simply cooked up my experimental data. That is, I am being unethical, which is a very, very serious happening. See, remember, making mistakes in the experiment is fine. But if I deliberately fudge my experimental results or deliberately copy someone's experiment and claim that it is my own, then this is a serious crime in the world of science. Making mistakes, no problems. If you have made a mistake and later on you find that this is a mistake and you report to the scientific world that, look, my past result was a mistake, then you will be honored because you are being honest. In science, there is no other way but to be honest, sincere, and be precise in your analysis. Okay. Coming back to the Nobel Prize, so Andrea Ghez of USA, she, along with her team, they used the Keck telescope in Hawaii and monitored the motion of stars around the Sagittarius A star. You see the here there is a star-shaped symbol. That star-shaped symbol is the location of the center of our galaxy. Okay, here is our center of the galaxy, and Andrea Ghez used, along with her collaborators, used the Keck telescope situated in Hawaii to monitor the motion of stars around the center, many stars from 1995 to about 2004. They accurately monitored many stars. Okay. And some of the stars you can see, they go very close. Look at the eccentric elliptical orbit of a star. The star going in an eccentric elliptical orbit. And its closest approach to the center is very tiny. Similarly, look at the eccentric orbit here. Look at the eccentric orbit here. They go very close to the central point. Similarly, Reinhard Genzel, they use the Very Large Telescope, European Very Large Telescope, in short form VLT, and his group members, they also did lot of accurate measurement of stellar position. So they were independently doing the observation so that they can compare with each other whether their results agree, and they therefore from the orbital studied a more refined version of Kepler's law technique. They could estimate the mass of the star, mass of the object at the center, and the mass they deduced, both the groups deduced independently, was around 4.5 million solar masses. In fact, if you look at the problem set, I have given problems concerning a star. I've of course taken it to be circular orbit, but actually in their analysis they had found highly eccentric orbit. I've given a problem where there is a star going around the Sagittarius A star uh, with a period, closest distance being 17 light hours. I've asked you to calculate the speed. Please do the problem. There were also stars for which the orbit was circular in nature. As you can see, there is a circular orbit for this star. And again, you can use the famous centripetal acceleration being provided by the gravitational force. So V square by R is gm by R square, so that V square is gm by R. And from that also, you can measure the velocity by monitoring over several years. You can measure the radius of the star orbit. From that, you can estimate the mass. Okay. And because both the groups, they used speckled interferometric technique, similarly speckled band, and similarly the adaptive optics to make position measurement of the stars very accurately. So we have come a long way from Tycho Brahe days. As you know, Tycho Brahe in the 17th century or 16th century, I've forgotten, he had made accurate position measurement of planets, because of which Kepler could give his three laws of planetary motion. And now you see, we are advanced so much, and that is what is the remarkable thing about human civilization, that now one can do much more accurate measurement of stars going around the central black hole of our Milky Way galaxy. And because of this Herculean effort, they were given the Nobel Prize this year. And for other objects like quasar, active galactic nuclei, there are other methods of finding out the supermassive black hole, but I'll pause for a while and look at the questions. Okay, so there are some questions. Let me take the question first, uh, that of Ankit Yadav. Can you repeat again this concept? Now, my question that was sitting in the board of the velocity increase, and same thing like after crossing out. Okay, okay, I'll talk about it, but before that, I'll go back to that slide, Ankit, and explain it better. Uh, Shivangi is asking, how do we know that mass of black hole increases with engulfing bodies? That's a very good question. Uh, there is no observational measurement that mass of a black hole is increasing with time, because as I've told, in astronomy the time scales are huge. When I talked about velocities, remember I told you about clusters of galaxies where galaxies move with extremely high velocities of the order of 1500 kilometers per second. You might think that with such high velocities, things will be varying fast. The answer is no, because the cluster of galaxy, the size is of the order of megaparsec. And to see changes, the object moving from one point to another, 1 megaparsec by 1500 kilometer per second, if you find out, you'll find that it is more than million years of time. So yes, black holes theoretically, as they swallow ambient matter, the mass of the black hole will increase, but the rate of increase is so tiny that with present day technology, we cannot find out at what rate the mass of the object is uh, increasing. To give you the actual reason why you can't find out, because remember, in any measurement there are errors. So when Andrea Ghez and Reinhard Genzel, when they are reporting the black hole, supermassive black hole mass at the center of our galaxy, the black hole mass comes with an error. And if the increase in the black hole mass by swallowing of stars, that rate is so small compared to the error bars, then we can't actually find out whether the mass is increasing or not. So these are experimental limitation. And that's the reason astronomers cannot directly measure the rate at which black hole mass is increasing because of swallowing of ambient matter. All right. Dinesh is asking, no, no, no. Dinesh, our solar system is very much within our Milky Way. As I told you, that solar system is only 8 kiloparsec from the center of our Milky Way, while the Milky Way, the stars and the gas, they are found for our Milky Way to as high a distance as 30 kiloparsec from the center of our galaxy. So therefore, our solar system is well within our Milky Way galaxy. Kushi Arora is saying that yes, you're right. In one of the detection, they found uh, a binary object coalescing to give rise to gravitational waves, and one of the object, its mass was uh, in excess of two solar mass. So whether it was a neutron star or a black hole, uh, people have not yet figured out. There's a question, because I told you that there is an upper limit to neutron star, and the upper limit is certainly 3 solar mass, but it lies between 2.3 to 3 solar mass. So we don't know whether the one of the components was a neutron star or a very low mass black hole. So a lot of analysis is going on currently regarding that LIGO event. Shubham is asking, well, no, the universe, according to classical general relativity, started from the singularity, but the universe is also expanding. And as it expands, the massive stars will become black holes and thereby the singularity. But these singularities are moving further away from each other because galaxies themselves are moving further away from each other. So, therefore, even though very massive stars will collapse into black holes, but they belong to galaxies and the galaxies are moving apart. So if the universe is in an expanding mode, as we inferred today, the universe will still be expanding and will be made out of black hole singularities as well as neutron stars as well as white dwarfs. Okay. All right. Khushi is asking, well, Hawking radiation, I will come to Hawking radiation soon. But as a part of general knowledge, let me tell all the students present is that Stephen Hawking, around 1974, when he did quantum theory near the event horizon of a black hole, showed theoretically that the event horizon, due to quantum effects, will actually radiate like a black body. In other words, Hawking demonstrated that truly speaking, when you take quantum effects into account, the event horizon is not dark, but event horizon will have a temperature. It's a very important uh, work, no doubt, but unfortunately, you can immediately show that for astrophysical black holes, the Hawking temperature, due to this quantum effects, is very tiny, less than 10 to the power minus 6 degree Kelvin. Such low temperature Hawking radiation cannot be detected. And because there was no direct evidence for Hawking radiation, Hawking never got a Nobel Prize for this work, but it was a landmark work uh, of all times. Right. So let me go back to um, Ankit's question and talk about the event horizon more. Right. So what I mentioned was that whenever you are having a vehicle, when you say that my car can move at a speed 180 kilometers per hour, but speed with respect to what? When my car moves with 180 kilometers per hour maximum speed, it moves with respect to the road. All right. Similarly, when I say that I am in a motorboat and the maximum velocity I can have of my motorboat is 100 miles per hour, what I mean is that I can travel at a speed 100 miles per hour with respect to water. Remember that it's with respect to the water. Hence, if I cross this dotted line, Remember, what are these dots? The locus of dots which form this line are the points at which the velocity of water in this direction is 100 miles per hour. So, if my boat is anywhere at this point and I use my motorboat with full throttle in the opposite direction, that means the water is moving in this direction with speed 100 kilometer, 100 miles per hour in this direction, but I am trying to move in the opposite direction with 100 miles per hour, but I am moving with respect to the water in the opposite direction. And the water here is moving in the rightwards direction. So, for an outside observer, the outsider observer will see me, if I am on any one of this point, to be at rest. Because with respect to the water, I am moving away at 100 miles per hour, but the water at these points is moving towards the right with 100 miles per hour. So, therefore, for the outside observer, my velocity, if I am on any of the points of the dotted line, will be zero. But the moment I cross the line towards the right, here the water velocity is more than 100 miles per hour in the rightward direction. So, with respect to water, when I move in the opposite direction with velocity 100 miles per hour, then I will be moving towards the right with respect to an outside observer. The outside observer will see me going towards the right and eventually falling along with the waterfall and disappearing. So, this is just an analogy for this dotted line acting as an event horizon. For the real black hole, there is no medium, there is no water. It is not that for a black hole, the space time itself is moving towards the singularity. So, I can't use this analogy to full accuracy when I talk about the event horizon of a black hole. It's not that for a black hole, for a black hole, it's not that the space time here, it is like water falling towards the singularity, and it's not that the event horizon, at the event horizon, the space time here itself is falling with speed c towards the black hole, and here the space time is falling with greater than speed c. Okay, that is not the case. That is the reason why this analogy has to be taken with a pinch of salt. Okay. Uh, as I said, uh, today I have some other engagement, so I would like to postpone the evening lectures to some other day. But since I have given you an assignment sheet, I would like to tell you I'd like to give you some hint how to do the first problem. In the first problem, I have said that you have a star which is in hydrostatic equilibrium, and if the star has mass m and radius r, and you have a core where the nuclear burning is taking place, the thermonuclear fusion is taking place in the core, and the core size is, let's say, uh, I've forgotten whether zero point 0.1 r or uh, 0.01 r. Let me just, yeah, I think it is 0.01 r. And I've asked you to calculate the core pressure. Now, this is a calculation which is order of magnitude calculation. It is not setting up the hydrodynamic equilibrium equation, because that will involve gradient of the pressure and all that kind of vector calculus. Not that. I want a very simple physical way of thinking. Of course, you will not get an accurate result. You'll get an order of magnitude estimate. And I'll give you a hint as to how to go about doing the problem. I've already given you a hint that by definition, a star, I mean, it's a accurate description. It's not true that the outside the boundary of the star, there is no matter. After all, for sun, we know above the sun's photosphere, there is a hot corona, although the density of the hot corona is very low compared to the density of sun. But nevertheless, there is some matter. But for the sake of simplicity, you can assume that the star of mass m and radius r outside, that means at distances greater than capital R, there is no matter. So therefore, the pressure is zero. If the core pressure is, let's say, PC, then what is the gradient in the pressure? It is PC minus zero. Okay, so it is PC itself. And therefore, what is the outward force exerted by the core on the rest of the matter? It is PC minus zero multiplied by 4 pi RC square, because 4 pi RC square is the surface area of the core, and pressure times area gives you the force, right? And because the star is in hydrostatic equilibrium, this outward force of pressure of the core multiplied by 4 pi RC square must balance the weight of the stellar matter above the core. So this is the hint. So you have to calculate what is the weight of the matter above the core, and the weight must be counteracted by the force due to pressure. And from that, you can calculate, or rather estimate, the core pressure. So please do all the problems. For the black hole problem, for the fluctuation, time scale fluctuation, uh, I have already told you how the fluctuating luminosity and the scale of time scale of fluctuation can tell you about the size of the emitting region. You can do all the exercises. By the way, during the lecture itself, I have asked you to calculate the Schwarzschild radius for many different um, astrophysical objects. Please do all the calculations, because unless you do the calculations, you'll not get a feel for the astrophysical quantities that will be relevant. Okay. Uh, right. But I think because we have already uh, overshot the time limit of 12:30, I will stop here. But please do all the problems, and next week we will discuss about the problem set. Okay, but uh, again, let us figure out what is a more convenient time for the uh, afternoon set of lectures, so that from next week onwards we have a fixed time for the afternoon set of lectures. Okay, all right. Are there any more questions? Well, if there are no more questions, I will end the broadcast. Uh, Soon I will respond to questions by Yashika and others regarding which portions of Frank Shu's book you must be studying regarding the present set of lectures. All right. So remember that we will meet again next Saturday. Till then, goodbye. But in the meantime, please do the problems given in the first assignment set. So, goodbye, everyone.